December 1942, high above the Solomon Islands. A 19-year-old waist gunner named Eddie Kowalski stands in the belly of a B-17 bomber, gripping a Browning M2 that shakes in his hands like a jackhammer. Out of the clouds, a Japanese Zero flashes across his 10-0 clock about 300 yards out, cutting through his field of vision like a dart. Eddie does exactly what instinct tells him. He centers the crosshairs on the enemy plane's fuselage and pulls the trigger. 50 rounds tear through the sky. Tracer fire streaks forward, and he watches every bullet miss, each one sliding harmlessly behind the Zero's tail. The Japanese pilot doesn't even flinch. He keeps flying untouched, while Eddie's ammo counter spins toward empty. This wasn't Eddie's failure. It was happening everywhere. Across every theater of World War II, gunners just like him, well-trained, determined, and armed with the best machine guns on Earth, were missing, not occasionally, constantly. In early 1943, the Army Air Forces launched a study analyzing gun camera footage from bombing missions over Europe and the Pacific. The findings were devastating. Trained aerial gunners were scoring less than 4% hits against moving targets. That meant for every 100 rounds fired at an enemy plane crossing their sights, 96 hit nothing but air. The math was merciless. A typical engagement lasted 8 to 12 seconds before the enemy broke away. The Browning M2 fired about 800 rounds per minute, around 13 per second. In a 10-second fight, a gunner could fire roughly 130 rounds. With a 4% hit rate, maybe 5 bullets would connect. 5 hits weren't enough to bring down a Zero, much less a rugged German Focke-Wulf FW-190. Enemy fighters could take dozens of 50-caliber hits and keep flying. The human cost was staggering. In 1943 alone, the 8th Air Force over Europe lost an average of 188 bombers per month. Each B-17 carried 10 men. That's 1,880 aircrew killed, captured, or missing every 30 days. Many of those losses came from bomber groups that simply couldn't defend themselves. The gunners were doing everything right, tracking targets, maintaining sight, firing in controlled bursts. The issue wasn't courage or training. It was physics, and physics didn't care about bravery. Every gunner aimed directly at what he could see. It felt logical. Point, shoot, hit. That works on a rifle range or when hunting a deer moving at 20 meters. But enemy fighters weren't deer. They were crossing the sky at over 300 mph. Some late-war jets, like the Me-262, exceeded 540 mph pace. At those speeds, by the time a bullet reached the target wasn't there anymore. A 50-caliber bullet left the Browning at about 2,900 feet per second. Almost instant, but not instant enough. At aerial ranges of 200 to 400 yards, time and distance changed everything. A Zero at 300 MARSM covered 440 feet every second. At 300 yards, 900 feet, a bullet needed about 0.31 seconds to reach its mark. In that time, the Zero had already moved another 136 feet forward, roughly 11 car lengths. So while gunners aimed at where the plane was, their bullets struck where it had been, passing harmlessly through empty air. This was known as deflection error. Scientists had long understood deflection in theory, but applying it in combat was another matter entirely. The required correction wasn't small, it was huge and counterintuitive. Against a target crossing at 90 degrees from 300 yards away, a gunner needed to aim 15 to 20 feet ahead of the aircraft's nose. That meant firing into what looked like empty sky and trusting the enemy would fly into the stream of bullets. Every instinct screamed against it. Gunnery instructors tried to teach this in training. At the Laredo Flexible Gunnery School in Texas, recruits studied deflection charts, fired from moving trucks, and used turret simulators. But it rarely translated to combat. Deflection wasn't a single number. It changed constantly with target speed, angle, distance, altitude, and even whether the target or bomber was turning, climbing, or diving. A ball turret gunner firing at a BF-109 head-on needed a totally different lead than when shooting from the side, and he had about 4 seconds to figure it out while being shot at, bouncing through flak and gasping through a fogged oxygen mask at 25,000 feet. The psychological battle was just as deadly. Gunners who tried to lead their targets often gave up after seeing tracers streak in front of the plane, believing they'd overcompensated. Next time, they'd aim closer, then closer still, until they were firing directly at the aircraft again. Gun camera footage from 1943 shows this same tragic pattern. First bursts with proper lead, then subsequent ones walking backward until tracers trailed behind the enemy. Losses kept mounting. During the October 1943 Schweinfurt missions, the 8th Air Force lost 20% of its bombers, 60 aircraft out of 291. Survivors returned with dead and wounded crewmen, shredded hydraulics, and engines spewing smoke. In debriefings, gunners all said the same thing. They'd been shooting. Their guns worked, but their bullets never connected. Something fundamental had to change, and fast. Because at those loss rates, the Allied bombing campaign would collapse long before it ever reached Berlin. The answer had been sitting in a filing cabinet since 1924, written by a man almost no combat aircrew had ever heard of, Lieutenant Colonel James Puckle, not the 18th century Puckle who invented the defense gun, but an American artillery officer with a gift for ballistics, had published a technical paper called The Problem of Lead in Aerial Gunnery while teaching at the Army S Field Artillery School. Puckle wasn't a detached academic. He'd served in France in World War I, seen the first awkward air combats, and understood that rising aircraft speeds would create a targeting crisis that ordinary marksmanship couldn't solve. His paper laid out the math with brutal clarity. Puckle showed that once aircraft speeds passed about 150 mph, required deflection angles would exceed human intuition. Against a plane crossing at 250 mph, a gunner would have to aim roughly 4 to 5 aircraft lengths ahead of what he could see. The paper included tables and charts listing required lead for every combination of target speed, range, and crossing angle. A 200-yard shot at 90 degrees against a 300 mph target needed about 47 feet of lead. At 400 yards, that jumped to 94 feet. The numbers were staggering. Puckle's conclusion was chilling. Without mechanical help, aerial gunners would be effectively useless within a decade. And then the Army filed the paper away. Through the 1920s and 1930s, aviation advanced rapidly, but gunnery training stayed rooted in World War I habits. Sight picture, trigger control, breath control, as if students were preparing for a rifle match instead of a three-dimensional fight at 300 mph. A few warned that something had to change, but they were dismissed. After all, Americans prided themselves on marksmanship. Daniel Boone, Sergeant York. Surely that tradition would carry over to the air. It didn't. When the United States entered World War II in December 1941, Army Air Forces gunnery training was catastrophically unprepared. The standard qualification lasted only 4 weeks. Students fired roughly 1,000 rounds total, mostly at stationary or slowly towed sleeves traveling around 150 mph in straight, predictable lines. No scenario matched the chaos of a FW-190 diving through a bomber box at 400 mph while rolling. Graduates shipped out, climbed into B-17s, flew to England or the Pacific, and often found their training worthless the first time a zero flashed across their sights. By mid-1942, desperate commanders began scouring old technical libraries for any help. Captain Robert Williams, assigned to the 8th Air Force Gunnery Analysis Section, found Puckle's 1924 paper in the archives at Wright Field. He read it in one sitting and sent a memo to his commander with 2 words underlined 3 times. Puckle had predicted the disaster 18 years earlier. His math still held. Hundreds of airmen had died because nobody had listened. If Puckle was right, the question wasn't whether the math worked. It was whether anything could be done. Teaching gunners to compute deflection angles under fire was impossible. The human brain couldn't do trigonometry at combat speed. If conscious calculation failed, maybe something else could. The British had already begun finding answers out of equal desperation in the summer of 1940. RAF Squadron 609, flying Spitfires from Middle Wallop, faced a similar gunnery crisis. Flight Lieutenant John Dundas reviewed gun camera footage and found hit rates against crossing BF-109s around 6%, 6 hits for every 100 rounds. Spitfire pilots burned their whole combat load and watched German fighters go home untouched. Squadron leader Horace Darley made a radical choice. In early August 1940, in the middle of the Battle of Britain when every fighter was needed, he grounded his squadron for 3 days and ran live fire experiments that broke RAF orthodoxy. Darley had been a clay pigeon shooter and knew the best shotgun marksmen didn't calculate lead, they felt it. Their brains handled target motion subconsciously, and their barrels moved ahead without conscious math. Could fighter pilots learn the same instinct? His test was simple. A Hurricane towed a banner across the range while Spitfire pilots made repeated firing passes, but Darley forbade the usual careful aiming. Instead, he told them, "Don't aim at the target. Track its motion. Begin firing while you're still turning to follow it. And let the motion of your aircraft create the lead. Fire into where your instincts say the target will be, not where your eyes say it is now." The first attempts were disastrous. Misses by 50 feet, tracers stitching empty air. He made them repeat it. 40 passes each, over 3 days. No ballistic lectures, no tables, just repetition and one rule. Fire while you're still moving, not after you've steadied on target. By the 3rd day, something changed. Hit rates rose, not enormously but meaningfully, from about 6% to roughly 12%. Doubling hits meant twice as many enemy aircraft damaged or killed, and many more fighters forced home unable to fly the next day. Darley documented the results and sent them to Fighter Command on 18 August 1940. He observed that the fastest learners weren't the best peacetime shooters. They were the pilots who could suppress the instinct to aim carefully and instead trust peripheral vision and motion sense. The conscious brain was too slow. The trick was to train the subconscious to produce correct lead automatically, much like a baseball player catching a fly ball without solving equations. Fighter Command circulated the findings, but adoption was patchy. Some squadrons embraced the technique and saw better kill ratios. Others dismissed it as unscientific. By early 1941, the method was quietly becoming common practice, even if manuals hadn't caught up. American observers in Britain took notes, but the U.S. faced a different problem. Fighter pilots could learn instinctive deflection because they controlled the whole airplane. Bomber waist gunners could not. A waist gunner stood in a fixed position, while the bomber flew straight and level through flak. He couldn't use aircraft motion to generate lead. If conscious calculation was too slow and instinctive motion wasn't available, the answer had to be mechanical. Enter MIT's Radiation Laboratory, Division 7, created in early 1942. The name was deliberate misdirection. Radiation suggested atomic work and helped keep secrecy while they built fire control systems. The division's leader, Dr. Charles Stark Draper, was a 40-year-old engineer who had spent the prior decade developing gyroscopic instruments for aircraft navigation. Draper saw the core of the problem. This wasn't about shooting, it was about prediction. A gunsight had to show the gunner not where the target was, but where it would be when the bullets arrived. From Draper's lab came the prototype Mark 14 computing gunsight, which began to take shape by July 1943. It looked like something out of science fiction, a reflector sight linked to a gyroscopic system weighing 28 pounds, powered by the aircraft's electrical generator. The gunner controlled it through a mechanical ranging dial. By adjusting it to match the target's wingspan, he gave the sight the range data it needed. Then, for about 2 seconds, he tracked the target, keeping it centered inside a small aiming circle. During those 2 seconds, the gyroscope measured the target's angular velocity, how fast it moved across the gunner's field of view. And here's where things got remarkable. The Mark 14 sight's internal mechanism used a series of cams and gears, an analog computer made entirely of machined metal, to solve the deflection equation in real time. It combined the gunner's range input, the gyroscope's velocity data, and the known ballistics of the 50 caliber round to calculate exactly how far ahead the guns needed to aim. The result appeared as a glowing reticle floating in space ahead of the target. The gunner no longer aimed at the aircraft itself, he aimed at the lighted dot. And if his ranging and tracking were correct, that dot showed precisely where to fire. The Mark 14 performed complex math that would take a human several minutes by hand, and it did it 30 times per second, constantly updating as distance and angle shifted. Testing at the Naval Air Station in Norfolk, Virginia in August 1943 produced results that seemed unreal. Gunners who D never exceeded 5% hit rates against moving targets instantly jumped to 18% on their first day using the Mark 14. After a week of practice, their accuracy passed 25%. That was a 5-fold improvement over manual aiming, meaning 5 times more enemy aircraft damaged or destroyed per mission. But manufacturing and installing tens of thousands of Mark 14 sights across the bomber fleet required time the Allies simply didn't have. Production only ramped up in early 1944, and priority went to newly built planes rather than older ones already in service. Most gunners flying through late 1943 and early 1944 still relied on basic iron or simple reflector sights with no computing capability. They needed something they could use immediately. No new equipment, no electrical upgrades. They needed a method that worked with what they already had. The breakthrough didn't come from engineers or scientists. It came from combat gunners themselves, particularly those fighting in the Pacific, where engagement ranges and visibility were far better than over Europe. Staff Sergeant William Bill Fleming, a waist gunner with the USS Lexington's Air Group, had flown 31 missions by March 1944 and survived 4 aircraft losses. Fleming wasn't an officer, had no college education, and couldn't have explained gyroscopic precession if his life depended on it. But he had fired over 40,000 rounds in combat and seen 7 enemy planes go down. He also kept a notebook. Inside were sketches of enemy aircraft, each marked with hand-drawn lines showing exactly where he'd aimed during successful hits. He measured his leads in plane lengths, 2 ahead, 3 ahead, instead of in feet or yards. On March 14, 1944, Fleming showed his notebook to Lieutenant Commander Edward Butch O'Hare during a debrief. O'Hare, already a Medal of Honor recipient and one of the Navy's top tacticians, immediately recognized what he was looking at: real-world deflection data gathered under combat conditions. He ordered Fleming to train every gunner in the air group, not with lectures, but with hands-on drills using what became known as the spot shooting method. Fleming had gunners take their positions while another crewman walked along the deck holding a model aircraft on a pole. As it flew by, Fleming coached them to lead their aim. 1 plane length for shallow angles, 2 for moderate, 3 or more for steep crossing shots. The key was giving gunners a visual reference they could instantly recall. Count the plane lengths ahead, then fire. The Lexington's gunnery officer, initially doubtful but willing to try anything, tested the method during operations near Truk Lagoon in March 1944. He compared ammunition and hit data from the previous 8 weeks with results after Fleming AS training, and the difference was undeniable. Before the program, gunners averaged 4.2 hits per 100 rounds against crossing targets. By late April, that number had more than doubled to 9.1. Word spread quickly across the Pacific Fleet. By May 1944, variations of Fleming's method were being taught aboard the Essex, Enterprise, and Bunker Hill. Each ship's gunnery officers refined the approach, but the principle stayed the same. Give gunners a simple visual system based on the target EP's apparent size, removing the need for conscious calculation. A gunner did not need to think about 0.3 seconds of bullet flight time. He just needed to remember 3 plane lengths ahead. It worked because it aligned with how human vision naturally functions. Our brains are excellent at comparing relative sizes, but poor at estimating absolute distances. Telling a gunner to lead by 50 feet meant nothing when he couldn't to visualize what 50 feet looked like at 300 yards. But 2 plane lengths ahead gave him an immediate intuitive reference. The enemy plane became its own ruler. The gunner just extended that length forward into empty sky. By mid-1944, the Army Air Forces adopted a similar concept called radius of action shooting. Training manuals began including diagrams showing proper lead distances in multiples of wingspan or fuselage length. The 8th Air Force Gunnery School in Lavenham, England, rebuilt its entire program around it by June 1944. Mission losses, while still high, began to fall. In July 1944, bomber loss rates dropped to 3.4% per mission compared to 5.2% the previous October, a difference that meant hundreds more airmen returned home alive. But knowing the method and applying it in combat were 2 different things. Even with training, the human mind worked against itself when the shooting began. Psychologists embedded with the Air Forces recorded this in 1944 interviews. The issue wasn't knowledge, gunners could recall the lead distances perfectly afterward, it was instinct. Under stress, that conscious skill vanished, replaced by raw reflex screaming, "Aim at the threat." Captain Harold Kleen, an Army psychologist at Bovington, studied this through gun camera footage and post-mission interviews. He identified a consistent pattern, a phenomenon he called threat fixation collapse. Gunners often began engagements using proper deflection, but as enemy fighters closed in and danger intensified, their aim would slowly drift backward until they were firing directly at, or even behind, the target. Kleen's data revealed that this collapse happened fastest during head-on attacks, where combined speeds exceeded 500 miles per hour, giving the gunner barely 2 seconds before the enemy opened fire. Under that level of stress, technique gave way to instinct. Rational calculation vanished, replaced by a primal reflex, point at the threat and pull the trigger. The only way to overcome this was through repetition, so extensive that deflection shooting became instinctive, operating at the same subconscious level as walking or catching a ball. But that kind of training required time the military didn't have in 1942 or 1943. By late 1944, however, as the Allies gained air superiority and training infrastructure expanded, gunnery schools finally extended their programs. What had once been a 4-week course grew to 8 weeks, then 10. Trainees now fired 5,000 rounds instead of 1,000, and more than half were aimed at moving targets traveling at realistic combat speeds. At the Naval Air Gunner School in Jacksonville, Florida, a new drill introduced in August 1944 proved especially effective. 50 caliber guns were mounted on motorized turrets capable of rapid rotation and elevation, while high-speed boats towed targets across the water at up to 60 miles per hour, shifting range and angle unpredictably. Trainees engaged these targets 50 to 70 times per day until leading became automatic. Instructors didn't shout corrections. They let students fire, check their patterns, adjust, and fire again. The subconscious learned faster through feedback than the conscious mind ever could through explanation. Footage of elite gunners who survived 30 or more missions revealed something extraordinary. Their deflection aim points remained steady, even under intense stress. When a German FW-190 dove into the formation with cannon fire flashing from its wings, these veterans kept their lead perfectly. Their conscious minds might have been convinced they were about to die, but their hands maintained the sight picture anyway. They had achieved what martial artists call mushin, or no mind, a state where action flows without conscious direction. But reaching that level required time and ammunition most gunners never received. The math of wartime training was unforgiving. Producing a true expert required 5,000 practice rounds and 10 weeks of intensive instruction. Yet the bomber offensive demanded 50,000 new gunners in 6 months. Compromises were inevitable. Most gunners entered combat still consciously aware of their technique, able to perform well when calm, but prone to collapse under sudden stress or chaotic conditions. This created a unique imbalance in combat effectiveness. A bomber formation's defensive power was an at-t evenly distributed. It depended on which specific gunners occupied which positions on which aircraft. A squadron with several veterans could repel attacks that might devastate a formation of newcomers. German fighter pilots learned to exploit this, targeting bombers whose fire was hesitant or poorly placed, while steering clear of formations where the defensive bursts were immediate, accurate, and overwhelming. The revolution in deflection shooting, born from British experiments and American necessity, didn't end with World War II. Its fundamental truth remained. You must aim where the target will be, not where it is. The Mark 14 computing gun sight evolved into the Mark 18, used through the Korean War, and later into digital fire control computers capable of processing dozens of variables at once. By Vietnam, fighters carried radar-assisted systems that performed deflection calculations automatically. The F-4 Phantom-S lead computing optical sight completed in microseconds what Draper AS mechanical gyroscopes once did in fractions of a second. Modern air combat has largely moved beyond guns altogether. Missiles now intercept at distances where deflection means leading by miles instead of feet. But the physics haven't changed, only the method. An AIM-120 AMRAAM missile uses inertial guidance and active radar to update its path toward where the target will be, running deflection math thousands of times per second. The F-22 Raptor's AN/APG-77 radar doesn't just track, it predicts, calculating future positions based on speed and acceleration, then positioning the aircraft and weapons accordingly. It is the same principle William Fleming discovered with hand-drawn sketches in 1944, now executed by computers performing trillions of calculations per second. Yet deflection fundamentals still live on in modern pilot training. At the Navy Fighter Weapons School, Top Gun, students still learn guns-only engagements. Not because they expect to dogfight with cannons, but because predicting where a moving target will be sharpens spatial awareness, essential to every form of aerial combat. A pilot who masters deflection shooting instinctively understands closure rates, lead pursuit curves, and angle off, all critical whether you're firing a cannon or lining up a missile shot. The lessons reach beyond aviation. Modern defense systems like the Phalanx CIWS on naval ships or the CRAM protecting ground bases are advanced, automated extensions of the same principle those 1943 gunners struggled with manually. The Phalanx fires 4,500 rounds per minute, 75 per second, while radar constantly recalculates lead and adjusts aim. It's performing the same correction Eddie Kowalski had to make over the Solomon Islands, only faster and without human hesitation. Even combat simulation games reflect this enduring truth. Titles like War Thunder and Digital Combat Simulator require players to lead moving targets manually, teaching the same counterintuitive principle. Aim where the target is going. New players repeat the mistakes of 1942 gunners, watching their tracers streak harmlessly behind enemy aircraft until instinct catches up with physics. The best players, like the best gunners, eventually achieve unconscious competence, their hands adjusting automatically, their minds silent. The leap from 4% hit rates in early 1943 to over 20% by late 1944 marked one of World War II's most dramatic tactical evolutions, not through superior machines but through mastering human cognition. Thousands of airmen who might have died returned home. Enemy fighters that once escaped fell in flames. Bombing campaigns that might have failed reached their targets, all because someone realized that instinct can be wrong, and survival depends on training the mind to trust physics instead. The gunners who learned to aim at empty sky, who dared to fire at nothing visible and believed their bullets would meet metal, proved something profound about human adaptability. We are not prisoners of instinct. With knowledge, repetition, and necessity, we can retrain ourselves to act against intuition and win. That lesson, written in blood over Europe and the Pacific, remains timeless wherever humans face a choice between what feels right and what truly works.